You ever stop to think about how our gadgets just keep getting faster? Like downloading massive games in, well, basically no time. Graphics cards making things look almost real. Even those super thin laptops have ridiculously fast drives now. It's kind of amazing how it all keeps up.
It really is. And the unsung hero behind all that speed, all that communication inside your computer is something called PCI Express. You'll often just hear it called PCIe.
PCIe, right. Okay, sounds important, like the plumbing. Or maybe the wiring. What's it actually doing in there?
Hey, plumbing's not bad. Think of it more like a dedicated superhighway system inside your PC. It gives all the important high-speed components, your graphics card, definitely those NVMe SSDs you mentioned, your network card, their own direct lanes to talk to the processor and the memory.
Ah, okay, so this isn't like those older slots we used to have, the white PCI ones, and AGP for graphics.
Exactly. PCIe was specifically designed to replace those older ways of connecting things. PCI, PCIX, which was a faster server version, and AGP. The big problem with those is they were parallel buses.
Parallel buses, meaning everyone shared the same road.
Pretty much, yeah. Multiple devices all had to share the same set of wires, the same communication lines, and as components got faster and needed more data, it just created, traffic jams, bottlenecks.
Right. Makes sense. So PCIe gives everyone their own express lane instead of making them all merge onto one highway.
That's the perfect analogy. It moved from that shared parallel setup to dedicated serial point-to-point connections. That was a real game changer.
Serial point-to-point, okay.
Yeah, each component gets its own direct link. And crucially, it can send and receive data at the same time. That's called full duplex. So much faster speeds, fewer actual wires needed. It just cleaned everything up and sped everything up enormously. Getting rid of that shared road was key.
Got it. Okay, so our mission for this deep dive then is to really get a handle on PCIe. Understand, the basics, how it's changed over the years to get so fast, and why it's just so critical for, well, everything computers do now, from gaming rigs to massive cloud servers, but maybe without needing an engineering degree.
Exactly. And honestly, understanding a bit about PCIe gives you real insight into how your own system works, and you start to appreciate why upgrades make such a difference. It demystifies things a bit.
All right, sounds good. So where do we start digging into this internal superhighway? What's the first stop?
Let's start with the basic structure. Like a lot of complex tech, PCIe uses a layered architecture. It breaks the job down into manageable pieces. It's actually pretty similar to how networking protocols like TCP/IP work, if you're familiar with that. Different layers handle different tasks.
Layers?
Okay.
Like different departments in a company?
That works too. Or levels in a building. PCIe basically has three main layers. There's the transaction layer at the top. Think of that as like the planning and dispatch office. Then the data link layer in the middle, the reliable courier service. And finally, the physical layer at the bottom, the actual roads and the trucks.
Roads and trucks. I like that. And this layered thing helps how?
It means each layer can focus on its job, and you can update or fix problems in one layer without messing up the others. It provides modularity.
Okay, let's start at the top then. The dispatch office transaction layer. What happens there?
Right, the transaction layer. It's responsible for generating and processing the actual communication messages, which are called transaction layer packets, or TLPs. These TLPs carry the requests like, hey, memory, I need this data. And the completions or responses, okay, here's the data you asked for.
So it's managing the actual conversations? What kind of things they're talking about?
All sorts, really. It deals with four main types of addresses inside the system. There's memory space for accessing RAM I/O space, or input-output for older ways of talking to peripherals. Then configuration space, which is super important for setting up devices when the computer boots. And finally, message space for special signals and interrupts.
Okay, and these TLPs, these packets, what's inside them? Like an address label?
Exactly. Every TLP has a header. That's the address label, the instructions. It says what kind of transaction it is, like a memory read or write, the address it's going to, how much data is involved, maybe its priority, all the critical info. Then usually there's a data payload. That's the actual stuff being sent if it's, say, a write request. And optionally, there can be something called an ECRC end-to-end cyclic redundancy check. It's like an extra seal on the package to make sure the data inside hasn't been messed up anywhere along its entire journey.
Okay, sounds pretty robust. How does it stop one component from just flooding another with too much data? Like sending too many packages at once?
Good question. That's handled by something called credit-based flow control. It's actually quite clever.
Credit-based?
Yeah. Imagine the receiving device tells the sending device, okay, I have space in my buffer for, say, 10 packages of this type and 5 packages of that type. Those are its credits. The sender keeps track of these credits and only sends a TLP if it knows the receiver has enough buffer space for it.
So it's like checking the recipient's mailbox size before sending something.
Exactly. It prevents the receiver's buffers from overflowing, which would cause chaos and data loss. It keeps everything orderly.
Makes sense. Okay, let's move down a level. The reliable courier service, the data link layer, what's its job?
So the data link layer sits between the transaction layer and the physical layer. Its whole purpose is ensuring reliable delivery of those TLPs across one specific link, that direct connection between two components.
Just one link at a time.
Right. It takes a TLP from the transaction layer upstairs, adds a sequence number like numbering the packages 1, 2, 3, and also adds another error check called an LCRC or link CRC. Then it hands this slightly modified packet down to the physical layer to be sent.
Sequence numbers and another error check. So it's like quality control for just that one hop.
Precisely. When a packet arrives at the other end of the link, the receiving data link layer checks that LCRC for errors and checks the sequence number to make sure packets arrived in order and none are missing.
And what if it finds a problem? A damaged package or one missing?
It uses a simple ACE-OK SIR protocol. ACK means acknowledged, I got it, it's okay. ATACE means negative acknowledge, something's wrong. If the receiver sends an ATAC, or if the sender doesn't get an ACK within a certain time, the sender automatically retransmits the packet from its own buffer. It keeps trying until it gets an ACK.
So it guarantees delivery on that specific link.
Exactly. It provides that link-level reliability. It also handles some other link management stuff using special small packets called DLLPs, data link layer packet.
DLLPs, what are they for?
They're only used for communication between the data link layers at each end of a link. They don't carry user data. They're used for sending those ACK6 we just talked about, for exchanging updates about those flow control credits, and also for managing link power states, which we can talk about later.
Okay, interesting. All right, down to the bottom layer, the physical layer, the roads and trucks. What's going on there?
This is where the digital ones and zeros become actual electrical signals traveling over wires. Its job is to physically transmit and receive the stream of bits that make up the packets.
How does it do that reliably at such high speeds?
It uses pairs of wires for each signal path, transmitting the data as a difference in voltage between those two wires. This is called differential signaling.
Differential. Why 2 wires?
Because it's much, much better at rejecting noise and interference. Any electrical noise that hits the wires tends to affect both wires in the pair equally, so the difference between them stays readable. This is absolutely critical for hitting those multi-gigabit speeds reliably.
Makes sense.
The physical layer itself is kind of split into 2 parts, an electrical subblock and a logical subblock. The electrical part has the actual transmitters and receivers, including a crucial component called a SerDes.
SerDes. Sounds like a sci-fi character.
Hey, maybe. It stands for serializer deserializer. Inside the chip, data is usually handled in parallel, like 8 bits or 16 bits at a time. The SerDes takes that parallel data, serializes it into a single stream of bits to send out over the PCIe lane, and then the SerDes on the receiving end does the opposite, deserializes the incoming stream back into parallel data for the chip to use.
Okay, got it. And the logical part of the physical layer?
The logical part handles things like, well, initializing the link, making sure both sides are ready to talk. This involves something called the Link Training and Status State Machine, or LTSSM.
LTSSM sounds complicated.
It is, but think of it as the formal handshake protocol. When a link first powers up or resets, the LTSSM guides the two devices through a negotiation process. They exchange special signals called training sequences TS1 and TS2 to figure out things like how many lanes they're going to use for this connection, the link width, and what speed they can both reliably run at.
So they agree on the terms before they start sending real data.
Exactly. And for the faster generations, Gen 3 and newer, this training process also includes something called equalization.
Equalization?
Right.
Like on a stereo?
Sort of. As signals travel really fast down circuit board traces and through connectors, they get distorted and weakened. Equalization is a process where the transmitter and receiver make tiny adjustments to the signal, pre-shaping it before sending or cleaning it up after receiving to compensate for those distortions. It's like fine-tuning the signal to make sure it's clear at the other end, especially at those really high speeds.
Wow, okay. You also mentioned encoding schemes earlier. Why do they need those?
Right. At these high speeds, you need to make sure the receiver can accurately figure out the timing of the incoming bits, essentially, where one bit ends and the next begins. Encoding schemes manipulate the data stream to guarantee enough signal transitions, changes from 0 to 1 or 1 to 0 for the receiver's clock recovery circuits to lock onto.
But doesn't that add extra bits overhead?
It does. Early PCIe Gen 1 and Gen 2 used 8B10B encoding. For every 8 bits of real data, it transmitted 10 bits, so 20% overhead, which isn't great.
Yeah, that seems like a lot.
It is. That's why PCIe Gen 3 was such a big deal. It moved to 128B130B encoding. Only 2 extra bits for every 128 bits of data, much, much more efficient. Less than 2% overhead. That allowed them to get a bigger real bandwidth boost, even though the raw signaling rate didn't quite double.
Clever.
And the newest generations, 6.0 and 7.0, are using even more advanced techniques. They use PAM4 signaling, which encodes 2 bits per signal transition instead of just 1, effectively doubling the data rate again without doubling the frequency. But PAM4 is more sensitive to noise, so they combine it with things like FLIT mode, fixed-size link transfer, and forward error correction, FEC, to ensure reliability while keeping overhead low. It's all about squeezing more data through efficiently.
Okay, I think I'm getting a feel for the layers and the physical side. So zooming out again, how do these point-to-point links actually form the network inside a typical computer?
Right, the topology. The absolute key is that point-to-point connection we keep mentioning. Unlike the old shared buses where everyone had to wait their turn, each PCIe device gets its own dedicated pathway. No contention, no waiting for the line to be free.
And it's full duplex, you said?
Yes, simultaneous send and receive on that dedicated link.
Okay. And the lanes? By 1 by 16?
Yeah.
How do they fit in?
A single PCIe lane consists of 2 pairs of differential wires. 1 pair for transmitting data, 1 pair for receiving. So even a single lane is full duplex. A PCIe link is formed by bundling 1 or more of these lanes together.
So a link width like by 1, by 4, by 8, or by 16 just tells you how many lanes are in that bundle?
Exactly. And the total bandwidth of the link is basically the bandwidth of 1 lane multiplied by the number of lanes. And that 16 link has 16 times the potential bandwidth of an I1 link of the same PCIe generation.
Which is why graphics cards usually want that big by 16 slot.
Precisely. They need the maximum possible bandwidth. But here's a common point of confusion.
Uh-oh, what's that?
The physical size of the slot on your motherboard doesn't always guarantee the number of electrical lanes connected to it. You might see, say, 3 long slots that all look like by 16 slots physically.
Yeah, I've seen that.
But when you check the motherboard manual, you find out only the top one is actually wired with all 16 lanes electrically. The second one might only have 8 lanes connected, running at by 8 speed, and the third might only have 4 lanes running at by 4.
Okay. So you really need to check the specs.
Absolutely. Always check the motherboard documentation to know the true electrical configuration of each slot.
Good tip. And can you put like a small by 1 card in a big by 16 slot?
Yep, that's another great feature. PCIe is designed so you can plug a card with fewer lanes, like a My1 network card or a by 4 SSD adapter, into a physically larger slot, like by 8 or by 16. The card and the slot will negotiate during that link training process and just use the number of lanes the card requires, in this case by 1 or by 4. Vary. You also see things like riser cables to reposition slots or bifurcation, where the motherboard BIOS lets you split the lanes of a single physical slot. For example, you could potentially configure a by 16 slot to act as 2 independent by 8 slots, or maybe 4 by 4 slots if the motherboard supports it. Gives you options for connecting multiple devices.
Interesting. Okay, so we have these links and lanes connecting devices. What's the central command post? The main hub?
That would be the root complex, usually just called the RC. Think of it as the root of the PCIe tree structure. It's typically built right into the CPU itself these days, or sometimes into the main motherboard chipset.
And what does the root complex do?
It's the bridge between the CPU, the system memory, and the entire PCIe fabric. It initiates most transactions on behalf of the CPU. It manages the whole hierarchy of PCIe devices. And critically, during boot up, it performs enumeration, the process of discovering all the connected PCIe devices, figuring out what they are, and assigning resources to them.
So it's the boss.
Pretty much. It has connection points called root ports, and those are where the PCIe links branch out to connect to switches or directly to endpoint devices.
Okay, so root complex at the center.
Yep.
What are the things we plug in, like the graphics card or the SSD? What are they called?
Those are the endpoints, or EPs. They sit at the ends of the branches in the PCIe tree. These are your actual functional devices. The GPU, the NVMe controller, the network interface controller, NIC, sound card, whatever it is.
And they can request data, too, or just respond.
Both. Endpoints can act as requesters, initiating a transaction, like an SSD controller asking to write data to memory, or as completers, responding to a request from the root complex, like returning data from the GPU's memory. And a single physical device, like a complex network card, might actually contain multiple logical functions, each appearing as a separate device to the system with its own unique ID.
A unique ID?
Yeah, called a BDF number bus device function. That's how the system keeps track of every logical PCIe function.
Okay. What if you need to connect more devices than you have root ports available directly from the root complex?
That's where PCIe switches come in. They act like intelligent hubs or routers within the PCIe network. A switch has one upstream port connecting back towards the root complex, or another switch, and multiple downstream ports to connect more endpoints or even other switches.
So they let you fan out the connections.
Exactly. They provide fan-out capability. They look at the address and the header of incoming TLPs and intelligently forward the packet only out the correct downstream port needed to reach the destination, rather than broadcasting it everywhere. This is essential for building larger, more complex PCIe systems, especially in servers.
Got it. And you mentioned bridges briefly before for older stuff.
Right. Bridges are specifically for connecting different bus types together. The most common example is a PCI to PCI PCI-X bridge.
Right.
If you have an old PCI card you still need to use, this bridge chip sits on a PCIe link and essentially translates the PCIe protocol into the older PCI or PCI-X protocol, allowing that legacy card to work in a modern system.
So mostly for backwards compatibility.
Primarily, yes.
This system seems really adaptable.
Yeah.
You also mentioned something about multi-root architectures. Sounds fancy.
Yeah, that's usually found in high-end servers or specialized systems. Instead of just one root complex connected to one CPU, you might have multiple CPUs, each with its own root complex and its own PCIe domain.
Why would you do that?
Performance, redundancy, connecting large systems. Technologies like non-transparent bridging, NTB, allow these different PCIe domains, these separate trees, to communicate directly with each other, maybe sharing access to certain devices while still keeping their main memory spaces separate and protected from each other. It can also be used for failover. If one root complex fails, another can potentially take over its devices.
Okay, so that's more advanced server territory.
Definitely. But it shows the flexibility.
Yeah.
You can build anything from a simple desktop with a root complex and a few endpoints, all the way up to these complex, interconnected server architectures, all using the same fundamental PCIe building blocks.
Right. It's quite scalable. Okay, let's circle back to the speed aspect, because that's a huge part of PCIe's story. You said each generation roughly doubles the speed per lane.
That's been the incredible trend, yes. The raw data rate, measured in gigatransfers per second, GTs, has roughly doubled with each major generation jump. And remember, the actual useful bandwidth depends on that data rate, the number of lanes by 1 by 16, and the efficiency of the encoding scheme used in that generation.
Right, that 128B, 130B encoding made a big difference in Gen 3. Can you maybe give us those example bandwidth numbers again, just to make it concrete?
Sure. So a common PCIe 3.0 by 16 slot, like for a graphics card a few years ago, gives you roughly 16 gigabytes per second of bandwidth in one direction.
Okay, 16 gigabytes.
Jump to PCIe 5.0 by 16, which is common in high-end systems today, and you're looking at around 64 gigabytes per second.
Wow, 4 times faster.
Yep. And the latest, PCIe 6.0 by 16, thanks to PM4 signaling, effectively delivers about 128 gigabytes per second, again, in one direction.
128 gigabytes. That's staggering. And the total bandwidth is double that because it's full duplex.
Correct. The aggregate bandwidth combining both directions is double those numbers.
It's amazing how they keep achieving these speeds.
Yeah.
You mentioned you had a table summarizing the generations.
Yes. It shows the progression clearly. PCIe 1.0 started at 2.5 GTs per lane back in 2003. Gen 2 went to 5 GTs. Gen 3 hit 8 GTs, but with that much better 128B, 130B encoding. Gen 4 doubled the rate to 16 GTs. Gen 5 doubled again to 32 GTs. Gen 6 hit 64 GTs using PM4, and the target for Gen 7 is another doubling to 128 GTs per lane. The table lays out the year, the rate, the encoding, the resulting bandwidth per lane, and for an by 16 link for each one.
That really illustrates the relentless progress.
It does. It also highlights how they've had to get smarter, moving from just increasing clock speeds to more efficient encoding and advanced signaling like PM4 to overcome the physical challenges of sending signals that fast over copper wires.
We've covered full duplex sending and receiving at once. What about latency? You said PCIe is low latency. Why does that matter so much?
Latency is just delay. the time it takes for data to get from point A to point B. Low latency is critical for responsiveness. Because PCIe uses direct point-to-point links, data doesn't have to wait for the bus to be free like in the old days. And the flow control helps prevent delays caused by congestion.
So things just feel faster.
Exactly. It's crucial for gaming. You don't want lag between your mouse click and the action on screen. It's vital for high-performance computing, real-time data analysis, AI model training, anywhere that minimizing delays directly impacts performance or the ability to process information quickly.
Okay. Now, something maybe more relevant for laptop users, power saving. You mentioned ASPM.
Yes, Active State Power Management, or ASPM. This is a key feature, especially for mobile devices, but it helps in desktops too. It allows a PCIe link to enter low-power states when it's idle, when no data is being actively transferred, even if the devices themselves are still on.
Saving battery life, essentially.
That's the main goal, yes. By powering down parts of the link temporarily, it reduces overall energy consumption.
Are there different levels of saving, like a light nap versus deep sleep?
That's a great way to put it. There are several states. L0 is the fully active, working state. Then there's L0s, the ES is for standby. It's a very light sleep state. Saves minimal power, but allows the link to wake up almost instantly.
Okay.
Then there's L1. This is a deeper sleep state where more of the link circuitry is powered down. It saves significantly more power than L0s, but takes a little longer to wake up. The exit latency is higher.
And you mentioned substates.
Yes, for even more savings, particularly useful in ultra-portable devices, there are L1 substates called L1.1 and L1.2. These allow even more components like clock generators and parts of the SerDes to be turned off, but they have the longest wake-up times.
So it's always that trade-off. More power saved means it takes longer to get back to full speed.
Exactly. You trade deeper power savings for higher exit latency. And sometimes, if the system or a specific device tries to use the deeper sleep states, like L1, too aggressively, it can cause issues. Maybe slight performance hiccups if the link takes too long to wake up, or sometimes even stability problems if the signaling isn't perfect upon wake up.
Is that why sometimes you see an option in the BIOS to disable ASPM?
Precisely. If someone is troubleshooting weird hangs or performance issues, especially with things like NVMe drives that need fast response times, disabling ASPM is sometimes recommended to see if it helps, though usually it works just fine.
Do you have a summary for these ASPM states too?
I do. A table showing the state name, L0, L00, L1, L1.1, L1.2, the relative power savings, the typical exit latency, how the state is entered, and the key characteristics.
Useful. Okay, another feature. Quality of service, QoS. You said PCIe can prioritize traffic. How does that work?
Yeah, QoS allows the system to give preferential treatment to certain types of data traffic over others. It uses two main concepts: traffic classes, TCs, and virtual channels, VCs.
TCs and VCs?
Think of a traffic class as a priority label you can attach to a TLP. There can be up to 8 TCs, typically numbered 0 to 7, with higher numbers maybe indicating higher priority. A virtual channel is like having multiple separate logical lanes within the same physical PCIe link. Each VC has its own buffers and its own flow control credits.
So you could have a high priority VC and a low priority VC on the same physical link.
Exactly. The system software, like the OS and drivers, can map different traffic classes onto different virtual channels. For instance, TC0, maybe best effort traffic, might go to VC0, while TC5, maybe critical latency sensitive traffic, might be mapped to VC1. Then the arbitration logic inside PCIe switches and the root complex will give preference to traffic on VC1 over traffic on VC0 when deciding which packet to send next.
So in theory, you could make sure your video stream doesn't sputter because someone started a big file copy.
That's the idea behind it, yes. Ensuring that high priority time-sensitive data gets through without being unduly delayed by lower priority bulk transfers.
Is this actually used much in, say, my home PC?
Honestly, not so much in typical consumer systems. While the PCIe spec defines multiple TCs and VCs, support for more than the default VC0 is actually optional. Many consumer chipsets and devices might only implement VC0 to save cost and complexity. Plus, there hasn't been widespread software ecosystem support to really take advantage of it in desktops. It's more relevant and more likely to be fully implemented in enterprise-grade networking or storage systems where managing traffic priorities is critical.
Okay, so the capability is there, but maybe not always turned on for everyday users. Got it. What about hot plugging, like adding a card while the PC is on?
Yes, PCIe supports hot plugging or hot swapping. This means you can, in theory, add or remove a PCIe card while the system is running without shutting down.
That sounds useful, especially for servers.
Exactly. It's a key feature for high availability systems where you want to minimize downtime for upgrades or replacing failed components, but
There's always a but.
yeah, hot plugging requires support at multiple levels. The motherboard hardware needs specific circuitry. The PCIe slot needs to be designed for it, often with staggered pins to ensure power and ground connect first. The operating system needs to understand how to detect and configure the new device on the fly. And the device driver also needs to support being loaded and unloaded dynamically.
So not something you should just try on any old desktop.
Definitely not, unless you know the system is explicitly designed for it. You'll mostly find it in servers or specialized chassis designed for hot swap modules. The connectors themselves have presence detect pins that signal to the system when a card is inserted or removed.
Okay. And lastly, under key features, error handling. We touched on the data link layer's ACK&K. Is there more to it?
Oh yes. Reliability is paramount. So you have the LCRC and sequence numbers at the data link layer, catching errors on each hop and triggering automatic replays. You also have that optional ECRC at the transaction layer, checking data integrity end to end. But beyond just detecting and correcting errors, PCIe has a mechanism called Advanced Error Reporting, or AER.
AER.
Yeah. It's a standardized way for devices to log and report errors in much greater detail than the basic mechanisms. It can distinguish between correctable errors, like a single-bit flip fixed by ECC memory on the card or a successful LCRC replay, and uncorrectable errors, which might be fatal or non-fatal. This detailed reporting is incredibly valuable for system administrators to diagnose problems, track the health of components, and improve overall system reliability, availability, and serviceability, what the industry calls RAS.
So it helps figure out why something might be going wrong, not just that it did go wrong.
Exactly. Much better diagnostic.
Okay, that's a really comprehensive look at the features. Let's shift gears slightly and look back at how we got here. You mentioned PCI, PCIX, AGP. What were their main limitations that drove the need for PCIe?
Right. So PCI was the standard for years, but it was a shared parallel bus. Everyone talked on the same set of wires and they had to take turns. As CPUs and peripherals got faster, that bus became the bottleneck.
A traffic jam.
Exactly. PCIX was an attempt to speed up PCI, mostly for servers, by increasing the clock speed and widening the bus, but it was still fundamentally a shared parallel bus, just a faster one. AGP was different. It was a dedicated point-to-point port just for graphics cards, recognizing their unique bandwidth needs. It was sort of a step towards PCIe, but only for graphics.
So PCIe took that point-to-point idea from AGP, but made it general purpose in serial.
Precisely. It ditched the shared parallel bus entirely, adopted serial point-to-point links, and built that layered architecture we discussed, creating a much more scalable, high-bandwidth solution for all types of peripherals.
And we've seen that incredible evolution through the generations since then. Can we just quickly recap the key milestone for each generation again, like the big change?
Sure. PCIe 1.0 around 2003 established the core serial point-to-point layered architecture at 2.5 GTs per lane. PCIe 2.0 around 2007 doubled the speed to 5 GTs. PCIe 3.0 around 2010, big jump, reached 8 GTs and introduced the much more efficient 128B, 130B encoding, nearly doubling effective bandwidth again.
Right, the encoding was key there.
Definitely. PCIe 4.0 around 2017 doubled the rate again to 16 GTs. PCIe 5.0 around 2019, another doubling to 32 GTs. PCIe 6.0 around 2022, introduced PAM4 signaling to reach 64 GTs, also added things like Fellow-T mode and FEC for reliability. And PCIe 7.0, expected around 2020-2026, targeting another double to 128 GTs, likely refining PM4 and FEC.
And through all that, backward compatibility is maintained.
Yes, that's been a cornerstone. You can generally plug a new card into an old slot or an old card into a new slot, and they'll negotiate down to the highest speed they both support. A Gen 5 card and a Gen 3 slot will run at Gen 3 speeds. A Gen 3 card and a Gen 5 slot will also run at Gen 3 speeds. It makes upgrades much smoother.
That's huge for users. Now, who actually manages all this? You mentioned PCI SIG.
Right, the PCI SIG. That stands for Peripheral Component Interconnect Special Interest Group. They are the industry consortium, the organization that defines and manages the PCIe specifications.
So they write the rule book.
Essentially, yes. It's a nonprofit group with, I think, over 900 member companies now. All the big names in tech are members. They have technical work groups that develop the specs, debate features, issue updates called ECNs, engineering change notices. They get input from all the member companies.
And they make sure things actually work together.
That's a huge part of their role. They run a compliance program. They hold regular compliance workshops where companies bring their prototype products for rigorous interoperability testing against the SMAC and against other vendors' equipment. Products that pass get listed on the official PCI SIG integrators list.
So that list gives you some confidence that a device actually meets the standard.
Exactly. The overall goal of PCI SIG is to keep PCIe an open, stable, reliable, and interoperable standard that the whole industry can build upon. They're the guardians, making sure it doesn't fragment into incompatible versions.
Okay, crucial role. So we know what it is, how it works, how it evolved. Let's talk applications. Where is PCIe absolutely essential today?
Everywhere, really, but the big ones. Definitely graphics cards, GPUs, modern gaming, AI, content creation. They all need that massive by 16 bandwidth.
For sure.
Storage is huge now, too, especially with NVMe SSDs. Connecting directly via PCIe lanes, often using that little M.2 slot, is what gives them those incredible speeds compared to older SATA drives.
Yeah, the difference is night and day.
Networking interface cards.
Yeah.
From the basic gigabit Ethernet on your motherboard all the way up to 10, 40, 100, even 400 and 800 gigabit Ethernet adapters in data centers, they all rely on PCIe to handle that fire hose of data. Same goes for things like fiber channel adapters or high-speed Wi-Fi cards.
Right. What else?
Then there's a whole host of other expansion cards. High-end sound cards, cards that add more USB or Thunderbolt ports, video capture cards for streamers, specialized accelerator cards. If it needs high speed or low latency, chances are it's using PCIe.
So it really is the backbone.
Yeah.
But what about driving new technologies? Where is PCIe pushing the boundaries?
Oh, it's critical for so many emerging fields. AI and machine learning absolutely depend on it. You need incredibly fast links between the CPUs, the massive GPUs or specialized AI accelerators, and the memory systems to train those huge models efficiently.
Yeah, I have that.
High-performance computing, HPC, same story. Connecting thousands of nodes in a supercomputer, accessing vast parallel file systems. It all runs on high-speed interconnects, and PCIe is often the on-system foundation. Data centers and cloud computing are constantly pushing PCIe for faster networking, faster storage access, and enabling new architectures like disaggregated infrastructure, where pools of storage or accelerators can be shared over a network fabric, often built on PCIe technology.
Disaggregated. Interesting. Even automotive. Advanced driver assistance systems, ADAS, process huge amounts of sensor data in real time, and modern car infotainment systems are getting incredibly complex. PCIe is finding its way in there too, and looking way out. Even quantum computers might use PCIe-based systems for control and reading out the quantum states. Wow, okay. So it's pretty fundamental to the future as well. What are the next big trends for PCIe itself, besides just getting faster with Gen 7?
Well, PCIe 7.0 and the push beyond it will continue, always chasing more bandwidth and efficiency. But people are also looking at how to deliver that speed. Over longer distances, electrical signaling gets really challenging. So there's ongoing research and development into using optical interconnects, sending data using light over fiber optic cables instead of electricity over copper. PCI SIG already has standards for external copper cabling, like CopperLink, but optical might be needed for the next big leaps in speed or distance.
Switching from electrons to photons.
Potentially, yes, especially for connections between racks or even between chips in the longer term. Another huge trend is Compute Express Link, or CXL. Yes, it's actually built on top of the PCIe physical layer using the same electricals and slots. But CXL adds protocols for cache coherency and allowing devices like accelerators or even pooled memory banks to share memory directly with the CPU in a much more efficient way than traditional PCIe allows. It's a really big deal for data centers and AI workloads.
So leveraging PCIe, but adding more smarts.
Exactly. And finally, security is always becoming more important. We'll likely see continued development and adoption of features like integrity and data encryption, IDE for PCIe, allowing data to be authenticated and encrypted as it travels across the PCIe link itself, protecting against physical snooping attacks.
Makes sense. Okay, so wrapping up this deep dive then. PCI Express is clearly way more than just slots on a motherboard. It's this fundamental, constantly evolving high-speed fabric that connects everything vital inside our computers, our servers, and increasingly other advanced tech too.
Absolutely. That shift to point-to-point serial links was revolutionary. The layered design makes it robust and adaptable, and features like the high bandwidth, low latency, power management with ASPM, the potential for QoS, error reporting, they all contribute to making it the incredibly successful and indispensable interconnect it is today.
It really is amazing stuff working behind the scenes. And thinking about PCI 7 aiming for 128 gigatransfers per second per lane, it just makes you wonder, doesn't it? What kind of completely new things, new applications, maybe even new types of devices will become possible when that kind of speed is commonplace? What bottlenecks will that remove that we don't even realize are bottlenecks today?
That's the fascinating question, isn't it? The possibilities are always expanding. And if you are curious and want to get into the real technical weeds, the PCI-SIG website is the place to go. They have all the official specs and a lot of technical resources available.
Excellent recommendation. It's definitely a space worth watching.